Hello guys, in this lecture I'm going to continue what we discussed last time regarding velocity and acceleration, and remember what we said last time regarding an object going with a constant velocity. So if I have this object going with a constant velocity along this path, right, what do you think will happen here? Do you think that it's going to have any accelerations? In reality, yes, it will actually. Why? Because we said the acceleration, right, as a vector is equal to dv over dt. So even though the magnitude of the velocity vector is constant, basically, meaning that the object is going with constant velocity, it will actually have an acceleration. All right. And in reality, these two accelerations are what? Or let's say this object basically is going along, a path like this, right? It will actually, its position basically, or its velocity vector basically is changing along the path, right? So this is your velocity vector. So it will actually have two acceleration. One acceleration is going to be along this this tangential line basically, and then we're going to call this guy as in magnitude. We're going to call this at is equal to dv over dt. Okay, and then this is going to be along this small unit vector, which we're going to call ut. And as a result of the velocity vector changing direction, we're going to have another component, which we're going to call an. So an is going to be in that direction, and the value of an will actually be equal to v squared over r, where r is that instantaneous radius of that can be basically tangent to the curve. Okay, and an as a vector is going to be along un. So we're going to define our unit vector un basically, which is always perpendicular to the tangent on the path. Okay, so ultimately you're going to have one acceleration vector, right? We're going to call this at ut. Essentially, at is the rate of change of your velocity, or the rate of change of the magnitude of the velocity along the curve, right? Plus it's going to have an, right, which is along un. And guys, an will always point toward the center of the circle, right? Because when you're going along the path, basically your v is always doing this, right? So you will always basically leaning toward the center of the circle, and dv minus dt is pointing toward the center of the circle, and an will always be pointing toward the center of the circle. You never want to put an on the other end. Okay, guys, so by the way, this is the first time that I'm using this tablet, so bear with me if I'm trying to still learn how to use it. Okay, let's go into, okay. So let me see something here. Okay. Okay. All right. So how about some applications? Basically, this is a highway interchange system, and let's say you are coming from this direction. All right. If you're basically making a turn like this, right? What risk basically do you have? So sometimes if you actually went on an intersection like that, or this interchange system, you will see basically signs here saying that, if you have a truck, basically the truck will actually may tip basically, and then they will literally kind of draw truck like that basically, right? And why is that? Basically, this is because of this normal acceleration. We're gonna have actually a few examples on that, but like we said, basically, if you are in the middle of this thing, basically, you're gonna have a tangential acceleration, and then you're gonna have a normal acceleration toward the center, right? So this guy is gonna be your an, and this guy is gonna be your 80. Okay, let me see. This is not worth typing anymore. And this guy is going to be your 80, right? I'm going to draw it here again. So you're going along this guy, you're going to have 80, and then you are going to have an. Okay, just to put this in perspective, guys, I want to just do a very small example on this, and why basically they actually put the sign here, right? And I'm going to actually basically use free body diagrams to kind of illustrate that. And I'm going to do that on a very basic problem. Very basic exercise. Basically, let's say you have you have basically a rope basically, and then you have a mass basically connected to it, and then you're kind of spinning this guy along the circle, right? You feel basically that there is a tension in the wire, right? Where is the tension in the wire coming from? Even though this could be moving at a constant velocity. So what we'll do is we're going to draw a free body diagram. This is a block. Basically, it has its weight mg, and then you have the tension in the cable, and this has to be equal to what are the accelerations that the block is receiving or is subject to. Basically, we only have one acceleration, right? And it's pointing toward the center of the circle, just like the tension. So here, basically, on the acceleration diagram, we're going to put m v squared over r. So that really kind of sums it up, right? So you always have the tension, or the force is going to be always in the same direction as the acceleration, right? That is why you have mv squared over r. So the tension will always be equal to mv squared over r, same direction, and it's going to be equal to the magnitude of mv squared over r. This is how you can find the tension. Okay, so I think in your high school, basically, you learn about kind of like fictitious forces, or they call it centripetal force or whatever. In our course, we're not going to do that. In our course, we will simply find the acceleration and the center of gravity. Here, we're dealing with a particle point. And what is the acceleration of that point? Basically, it's simply mv squared over r, right? Don't forget the m, basically, right? When you put your acceleration on the acceleration diagram. There has to be a force that is equal to this, right? So T is going to be equal to mv squared over. How about mg in this case? How would you calculate mg? Well, you're gonna basically you will sum the forces, and you will actually have as well mat at the bottom, right? But literally, actually, when you are spinning this guy, it will actually kind of make an angle, right? It will not be a horizontal. It will be like that, basically, right? And so portion of the T will take care of the mg. So you won't actually have any acceleration like that, because in reality, your T is not very horizontal. Your T will actually have some very small angle. So this is going to be my T in reality. And this T basically is going to take care of, basically of your mg. So we won't actually have, so at steady state, basically, you will actually not have any acceleration here, right? Because this guy is going to be rotating in a along a circle, basically, right? That is not basically changing. All right, very good. So this is it regarding that. So I'm gonna jump into another. Okay. So here, let's look into some applications of that. If you have a motorcycle that is traveling uphill, right, for which a path can be approximated by this function. If the motorcycle starts from rest and then increases its speed at a constant rate, how can we determine its velocity and acceleration at the top of the hill? Right? How can we find its velocity and acceleration? How would we analyze this movement? So we know basically that the motorcycle is starting from rest and then it's increasing its speed at a constant rate. Right? How can we find its velocity and acceleration? Let's say you find its, we know, right? The velocity, right, will always be equal to only tangential acceleration, right? So if it's increasing at a constant rate, basically acceleration is constant. So we're going to say, okay, not sure why this is showing up here. Okay, so here the velocity at any instant basically is going to be equal to at times t, right? Because we integrate tangential acceleration, and then v is going to be equal to at times t. Okay, how about the acceleration at this point? Acceleration at that point, an is going to be equal to how much? It's going to be equal to v squared over r, right? And how can I find the radius of curvature here? We'll actually have an equation that for any given path, basically, we are going to be able to find the radius at that x. So if you actually have your x and then your y, and then you have some weird path, basically, at any x, basically, you will be able to actually find that circle that will actually fit into this curve, right? And then we're going to call this guy r of x. Okay, how do you find r of x? Well, I'm going to show you in a second. Okay, but this is the idea, right? So you find your tangential velocity from your tangential acceleration, or the acceleration along the movement, right? And then your normal acceleration is only related to your velocity, right? Only your velocity squared divided by r, where r is basically the radius of curvature, basically, at that point. Okay, this is what I just described earlier. So you'll have ut and then un. Remember, un will always be basically perpendicular to the tangent on a circle. So at every part of the curve, basically, you can have a tangent, right? There's only one tangent at every point. Like imagine, like basically, you're trying to put like like a ruler or something around the curve. Basically, it will only touch at one point, right? So at every point, you can only put the ruler at only one situation, right? And you're going to be able to do it perpendicular, so UN will always be along that, right? And then UT is going to be along that. So just remember those. Very important, but also it's actually very simple as well. It's not that complicated. Okay, so this is what we just did. So this is called R. Basically, is called radius of curvature, and sometimes in this book, basically, they refer to it as rho. Let me just change the color and then make this red if I can here. Let's see. Here we go. Let's jump in a little bit more. So we said V will always be toward or in the direction of the tangential vector ut. Okay, let's do here a little bit more, and then this is your velocity. Okay, I'm not gonna ask you guys to find y an is actually equal to v squared over r, but you just need to know this equation, right? Basically, the acceleration has two components. One component along the tangential vector, right, that is tangent to the path, and then another vector that is normal to the path, and then I'm gonna call this guy v squared over r. Okay, the actual magnitude, right, of the acceleration ultimately will be you're doing the square root of both of them, right? This equation also always applies, right? If you have the acceleration along the curve, right, you do at ds is equal to v dv. Basically, if I tell you that you're basically measuring ds along the curve, you'll be able to find the velocity at this point, right? Provided that s is basically along the curve, right? You're actually getting that distance. So this basically applies, this equation applies along the path, right? Okay, very good. And what happens if the radius of curvature basically goes toward infinity? Basically, n will be 0, right? Which kind of makes sense, right? So if you have a very large circle, basically r is going to increase, right? So the larger the r, basically, this guy is going to look like that, and then ultimately it's going to be like this, right? For a very huge radius. And then here, basically, an is going to be 0, right? Why? Because it's equal to v squared over r. R is very large, which makes sense, right? So if the radius is large, it means that the velocity vector is not changing direction a lot. So therefore, an is going to be 0. I'm pretty sure, I think by now you guys have already got the concept and are ready to start doing some problems, except you still need one more equation, which is the radius of curvature, right? I just mentioned to you guys earlier. So this is the equation that we'll use. So if you have, right, if I gave you, y as a function of x, y as a function of x, so this is your y, that could be like, a parabola, an exponent function, whatever it is, you will be able to get the rho based on that, right? So first derivative squared divided by that. So this is the radius as a function of x. Yeah, and basically at every point x, you are able to find the radius of curvature, and then the radius of curvature basically is going to be this one in this case, right? So if you do this circle, basically this is your radius of curvature. And then an is going to be along the center of this guy. Okay, guys, this is very important for you guys. Okay, I'm not sure why it's doing this line, but here you go. Okay, okay, so this is not much here. Okay, so let's start with one example. Let's determine the maximum constant speed a race car can have if the acceleration of the car cannot exceed 7.5 meters per second. We're having a radius of curvature of 200 meters. So the maximum constant speed. Okay, so here maximum constant. So if you have a race car, okay, it's trying to execute this curve basically, and then we know the radius here. Radius here is 200 meters. Okay, what is the maximum constant speed? How can we determine that? If the maximum acceleration, so what is the acceleration in this case? An is going to be, A is going to be equal to what? At, right, times ut plus an times un, right? What is at in this case? At is 0. Why? Because they tell you that the car is going at a constant speed, right? What is an? An is going to be equal to v squared over r un. Okay, so they are asking us for the maximum velocity if the acceleration cannot exceed 7.5 meters per second. So 7.5 meter per second square is going to be equal to v square divide by 200, right? So we can basically find v is going to be equal to square root of 7.5 times 200, right? That is a meter per second. Really nice, and then very basic stuff. Okay, let's do one more example. All right, so here we have a motorcycle that is traveling at 1 meter per second when it is at A. So here basically you were at 1 meter per second if the speed is increased by v prime, right? So v prime, this is like more like what? This is AT. You guys agree? AT is equal to 0.1 meter per second squared. Determine its speed and acceleration at the instant t is equal to 5 seconds. So we would like to find v at 5 and a at 5. All right, so how do we do that? So it's traveling at 1 meter per second initially, right? If the speed is then increased at this guy, at this acceleration, we need to find its speed and acceleration at t is equal to 5. Okay, how can I find? So it's starting from 0. How can I find the velocity at 5 seconds, right? If it is traveling with a constant velocity. So we're gonna say that v, right, is going to be equal to AT plus V0, right? Because here your acceleration is constant, right? So V is going to equal to 0.1 times T plus 0. So V at 5 is going to be equal to 0.1 times 5, which is equal to how much? 0.5 meter per second. So now we know at T is equal to 5 seconds, basically we found, so T is equal to 5, let's say you're here. Basically your velocity is equal to 0.5 meter per second. Oops. Okay, 0.5 meter per second. So now we need to find A, right? So we know what is A. What is A is going to be equal to AT times UT plus AN times UN. And by the way, when it's a unit vector, usually you want to put like something like that. What is AT? Do we know AT? Well, we do, right? AT is equal to how much? 0.1 meter per second squared. How about AN? So AN is going to be equal to how much? V squared over R. Do I know V? Yes, it's going to be equal, velocity is equal to 0.5 squared divided by R. So we still need to know R at T is equal to 5, right? Because the radius of rotation, the radius of curvature is basically changing. So in order for you to do that, you have to be able to actually calculate what X is. And, you know, how do you, maybe we can actually calculate S, right? We can calculate S by kind of doing the integration of V, right? So we know S is have to be equal to 1 over 2 AT squared because you have a constant acceleration, right? So S is going to be equal to 1 over 2, 0.1 times 5 squared. So once you calculate S, you want to be able to calculate X. And once you calculate X, right, you have the function, you have the equation of this guy, you can find the radius of curvature of here. And then once you find R, basically you will have AN. All right, I'm not gonna solve this now. I want you guys to actually work on this, and then we're gonna solve it together on Monday. All right, so I would like you guys to think about this, right? You have this X position. So if you have, you know, a curve basically, right? You were able to, you know, the value for X. I'm sorry, you know the value for S. How can you actually get X on that? And once you get X, basically we use which equation? We use this equation, right? Here we know y of x is equal to 0.5x squared, right? So we know first derivative, you know, here's the second derivative, etc. But you need to know x, right? So I'm gonna let you guys work on that, and we'll catch up on Monday for this.